Okay, so what we're going to do is I'm going to give you, we're going to do one more, find the eigenvalues of 3 by 3. Okay. So question 1, given A equals okay, so find the eigenvalues. So we'll do one more right from the start. This would be more like a final exam type question where the eigenvalues are going to be easier to find. The polynomial is not going to be really tricky. So step 1 when we're trying to find the eigenvalues is to find the matrix A minus lambda I, which is just subtracting lambda from the diagonal. So we'll have minus 1 minus lambda, 2 minus lambda, minus 1 minus lambda. Okay, so that's A minus lambda I, just subtracting lambda from that main diagonal. And then what do we need to do? Find the determinant of that. So you don't always have to do row operations like we did in the other examples last time. You notice that we've got two options here. We've got one row. Row 2 has 2 zeros in it. And also this row has this column has 2 zeros. Right? So we could do Laplace along either row 2 or column 3, and it would just involve one operation. It wouldn't have a lot to it. So let's do that. So let's suppose we take row 2. We're going to do Laplace along row 2. It's also a review of how to do Laplace. So that is, you take that element, 2 minus, well, all of them, but these are 0. So we don't need those. And then we multiply by minus 1 to the, whatever the place is that it's in. And this is the second row in the second column, so 2 plus 2 is 4. Or, like I said, you could just write all the signs in and decide, like plus, that's minus, plus, minus, right? They just all change as you go. So that's a plus sign. Times the determinant of the minor. So that is found by crossing off that row and that column, whatever's left. 2 and minus 1 minus lambda. So minus 1 to the 4 is just plus 1. And the determinant here, minus 1 minus lambda times minus 1 minus lambda. And then minus 0. And it's already factored. And that is called the characteristic polynomial. So when you're asked to find the characteristic polynomial, that's where you would stop. You don't need to work it out so that it looks like a polynomial. Even though it's factored, it still is a polynomial. See, that's fine, just like that. Okay, that's the characteristic polynomial. And we use the characteristic polynomial, set it equal to 0, solve for lambda, and that would be your eigenvalues. So here, 2 minus lambda equals 0 gives me lambda is 2, and minus 1 minus lambda gives me lambda is minus 1. So those would be the two. Okay. Now, in the diagonalization chapter, I don't know if you looked at it again or even remember what we talked about last time, but we said in order to diagonalize a matrix, to be able to diagonalize it, we need to have what? This is a 3 by 3. A was a 3 by 3. Do you need to have 3 distinct eigenvalues? No. What do you need 3 of? Eigenvectors. And one of these could have 2, so it could still be able to be diagonalized. You don't know until you actually find the vectors. And then you need, one of them would have to have 2 vectors and the other would have to have 1. And that would be 3 distinct vectors. So the values themselves don't tell you if it can be diagonalized. It's the number of vectors. Okay? So if we were to find the eigenvectors, so let's remember how to do that. Lambda equals 2. You plug that into a minus lambda I and row reduce. So I can just go back here. There's a minus lambda I. So I'm just going to plug into everywhere there's a lambda. Minus 1 minus 2 is minus 3. And usually the row operation, this already has a row of zeros, but usually the row operations are easy. There's not too many to do. Here we would take, say, row 1 and divide that by negative 3 to get a 1 in that top corner. And we could also switch row 2 with row 3 so that that row of zeros is at the bottom. Okay, and then our next step, we want this to be a 0, so that's in row 2. It's a 2, so we want the 1 to be a negative 2. And if we do that step, okay, what would be our next? This 3. So this will be row 2. It will be row 2 divided by 3. And then what? The minus 1 above. So that's in row 1. It's a minus 1, so this needs to be a positive 1. It already is. So row 2 plus row 1. And that will okay. So this is x, y, z. So if we take this out, we get x minus z equals 0, y minus z equals 0, and z would be free because these two have a lead 1. So z is t. So our solution would be x equals z, y equals z, and z equals t. Plug the t in. Now, that's not that's all the eigenvectors. We can put any t in and get another eigenvector. So 2, 2, 2 would be an eigenvector, 3, 3, 3. They would all be an eigenvector giving you the eigenvalue of 2. How would you check that that is, you did the row reduction right and it is in fact 1, 1, 1 for that? How would you check that? So remember, an eigenvector is a vector that when you multiply it by your original A, you get lambda times that same vector. Right? So how would we check it? If we take A, multiply it by x, by a vector, any of them, 2, 2, 2, 3, 3, 3, 100, 100, 100, it'll all work. And what should we get as our answer? What was lambda? 2. So what should we get as the answer when we multiply this? 2 times the vector. So we should get 2, 2, 2. So minus 1 plus 3 is 2. 2, 2 plus 1 minus 1 is 2. Right? So that would be a check if you just multiply. You should get that as the answer. Okay, our second eigenvalue was -1. Do the same thing, plug it into A minus lambda I. So minus 1 minus a minus 1 is 0. Augment it with zeros, and then row reduce. Yep. When you're going to find an inverse. Yeah. Okay, so what should we do here? We want a 1 in the top corner, so what would be our only first move? Yeah, change row 3 and row 1 so that you have a number in that top corner. You can't have a 0 then. So that would be our first 2, 1, 0, 0. So we want this to be a 1. So divide by whatever number's there. These rows are the same, so one of them will end up being 0. And you could just put that in if you wanted to. All right, next would be make a 1 here, because the rest of that column was already zeros. So this is row 2. We want to divide it by 3. Okay. Oh. Yep. Okay. Now what? So this is a 1. Yep. And the 3 above and below. Right. So row 1 would be, that's a positive half, so the 1 needs to be a negative half. And here is a 3, so the 1 needs to be a negative 3. And if we do those 2 steps, you get this. So how many free variables are here? This has a lead. This has a lead, so this one's free. So here we have what? X equals 0, Y equals 0, and Z is free. So our eigenvectors look like 0, 0, 1. And you could check. You take A and multiply it by our vector we just found. So A whoops. This gives me 0, 0, minus 1. Which is that vector times minus 1, and minus 1 was the eigenvalue we used. So that's what should have happened. Okay, so my question is, so we just took a 3 by 3, we found the eigenvalues, there were 2. I said that that doesn't mean you can't diagonalize, you just need to have 3 vectors, or 3 you need to, and we didn't have 3 vectors. We only had 1 for the first one, right here, and we only had 1 for the second one. You'd have to have 2 free variables for it to work. So this only has 2 independent vectors, so that means that it cannot be diagonalized. So since A has only 2 distinct eigenvectors, not values. The values didn't matter. It could have still worked. Then A cannot be diagonalized. And just before we do something that can be diagonalized, I have one other question. So, given okay, so I give you A, and I'm telling you that the eigenvalues are, for this one, 1 and 3. So you could use this as practice as well, because I just told you what the eigenvalues are. So if you wanted to practice before the exam, this one you know the answers to. So 1 and 3 are the eigenvalues. What are the possible characteristic polynomials? So you don't need to find the characteristic polynomial of this. Remember, the characteristic polynomial is, you know, something factored is equal to 0. We were given 2 values. So if lambda equals 1 is one of them, then lambda minus 1 would have to be one of the roots, or one of the factors. And if 3 is the other one, then lambda minus 3 would have to be the other. Now this is a 3 by 3, so that means it's a cubic function. So what are the possible, this is not a possible characteristic polynomial because this is a 3 by 3, but these are the only 2 factors because there was only 2 roots. So how could we make this into a cubic without adding another factor? Square one of them. Right, so this or that. And we don't know which one unless we actually went through and found it, right? But that would be your 2 possible. So what if I said it doesn't, but what if I said it only has lambda equals 1? What would be the characteristic polynomial? It would have to be lambda minus 1 cubed. That would be the only possibility. Because it has to be a cube if it's a 3 by 3. And right, so those would be the possibilities. Okay. So that's all that question. There's one like that in the homework. I just noticed a few of them have questions like that. So this one also I'm going to just give you, so for later practice. When we have lambda equals 1, the eigenvector is -1, 0, 1. And for lambda equals 3, the eigenvector is 1, 0, 1. So you can try that later and see if you get the right answer. Okay? So, and it can't be diagonalized because there's not 3. Okay. All right, so let's do one that can be diagonalized. Okay, so A equals I didn't make very good notes here. Really bad, in fact. Just a sec. Okay. Okay. I didn't write the original matrix down, and I did all the work, so I'm trying to go backwards and figure out what the original matrix. So my notes were not very good. I've got the end of the question, but not the start written down. I'm pretty sure that's it. We'll know in a minute. But, okay, so here it is. Now, we've got a whole row of zeros. What does that mean? What if I just ask the determinant of this question? Nothing to do with eigenvalues or vectors. Zero. Right. Okay, but if we wanted to find the eigenvalues, first find A minus lambda I. So subtract lambda down the diagonal. And then we want to find the determinant of that. So I've got two zeros in a row here, so we'll do that one. So here we would say minus lambda, that's minus 1 to the, that's the second row, second column, so 4, 2 plus 2. And then the determinant of what's left when we cross out those two. So 4 minus lambda, 3 minus 6 and minus 5 minus lambda. So minus 1 to the 4 is just positive 1. So this will be 4 minus lambda times minus 5 minus lambda minus a minus 18. So plus 18. So in order to factor this that's in the square bracket, we need to make it into a polynomial, and then we would factor that. So this will be minus 20 minus 4 lambda plus 5 lambda plus lambda squared plus 18. So lambda squared plus lambda minus 2. There. So this has 3 eigenvalues, so it's going to end up with 3 eigenvectors unless one of them had 2. If one of them had 2, then it wouldn't be diagonalizable either. So this is our characteristic polynomial. And from that we can find our eigenvalues, which they are lambda equals 0, lambda equals 1, and lambda equals negative 2. Yeah, well, this is a 0 property when you factor something. Like, what would make this equal to 0? Well, if this were a 0, then 0 times anything is 0. If this one were 0, then it wouldn't matter what these two are. And then if that one's 0, so it's a 0 property. Okay, so we've got our 3. And then we are going to find our vectors I'm going to show you one and then give you the other two. Okay, so if we did lambda equals 0, so we plug that into a minus lambda I, which we can still see right here. You can't, right there. So I'm going to plug 0 in here. So we'll actually go back to where we started with our A. Oops, plus 6 minus 5. Augment that with zeros, and then we row reduce. So if we switch this around and row reduce, we are going to end up with this. So you can do all your row operations. Okay. So x, y, z. So x plus z equals 0, and y plus 1/3 z equals 0. And z would be free. Okay, and I wanted to show you this one because, okay, so here's our eigenvector, okay, that we get when we row reduce. You'll find that no book would use this eigenvector because remember, this is all of the ones that are multiplied by any number. So this is one eigenvector, but if we multiplied this eigenvector by 3, that would be another eigenvector that wouldn't have fractions in it. So you'll notice that in any book, when they actually use it, they would get rid of the fractions. So they would say multiply this by 3, and we would use the eigenvector this, or even minus 3 and have more positives than negatives. You could multiply by 6 and get rid of it. You can use any eigenvector, right? So it could be any multiple of this, and usually if you end up with fractions in it, you get rid of them. That's the more standard way to do it. So you'll see in any book, they don't actually ever, when they diagonalize, they don't use a vector with fractions in it. They'll get rid of the fractions and then use that eigenvector instead, okay? So you could say that the eigenvectors are the vectors of this form. That's still right. It just isn't the exact one you got when you row reduced, but it's still an eigenvector. And any multiple of that works as well. Okay, so that was for lambda equals 0. Lambda equals 1 gives us I'm just writing down the row reduced. Okay, so you plug that in and then row reduce. So we get x plus z equals 0 and y equals 0. So this one would be free. Even though it's a 1, it's still free because it's not a lead one. It's not the first one in the row. So you'd say x is minus t, y is 0, and z is t. Okay, and that doesn't have fractions, so we would use that. And then if you found for -2, I'll write the row reduced one again, is there. So x plus 1/2 z and y equals 0. So we're not going to use this one. We'll multiply it by 2 because that one had fractions in it. So what would we get if we multiplied that by 2? Negative 1, 2 times 0 is 0, and 2. So we'll use this instead. Okay, so is A diagonalizable? So we had 3 eigenvalues. And each had 1 eigenvector. And they're all different. They have to be distinct. They can't be the same. But they wouldn't be anyway, because when you multiply by A, you have to end up with the same eigenvalue. So we have 3, so it's diagonalizable. Yes, since 3 distinct eigenvectors. Okay, so we'll do it. All right. So to diagonalize A, you can choose any order that you like. We'll just put them in the order that I have them written down. But if you had factored it, or you had found the eigenvector for 1 first, then you might have them in a different order, and it will still work no matter what order you put them in. Okay, so the order doesn't matter. So to diagonalize, we're finding matrix P and D, so that A times P is the same as P times D. And it turns out that the diagonal is found by taking the eigenvectors and putting them on the main diagonal. So 0, 1, negative 2. So the order doesn't matter, but the order the same for D and P. So if we put 0 first, the eigenvector for 0 has to go first in the P. So the eigenvector for 0, 0, 0 was -3, -1, 3. The eigenvector for 1 was -1, 0, 1. And the eigenvector for negative 2 is -1, 0, 2. So this was 0, 1, and negative 2, and then these were the same 0, 1, and negative 2, but the vectors. You could use the ones with fractions in it. It would still work, okay? Or you could multiply them by something different than I multiplied them, but it would still work. We could put, instead of -1, 0, 1, you could put -50, 0, 50. Like you multiply that row by 50, it will still work, okay? So any one eigenvector that's associated with that, but they just have to be kept in the same order. Now, at this point, you've done a lot of work. You can check, especially on a final exam. The final exam's worth, what, 55%? So once you get your eigenvectors, you should just check, are they right? Before I go on, I can do that row reduction again, if they weren't right, so that you get the same. How do you check them? You multiply by A, make sure that you got the 0. You multiply it by A by this, and you'll get the same thing, because it'll be 1 times that, and here you'll get that times 2. Okay, so you can check those. Then You do this, and then you can check this. Then you'll know you did everything right up to this point, because how do you check this? Right here, A times P should give you P times D. Okay? Now, if we solve for A, so A times P equals P times D. So to solve for A, we need to multiply by P inverse on the end. And if you put P inverse on the end of one side, you put it on the end of the other side. So these cancel, because that's equal to I. Okay. So here you could do this to check, but you don't want to. Why not? If we wanted to check that the P and the D are correct and we use this, you have to first find the inverse. And it's an inverse of a 3 by 3. Right, so you don't want to do that, okay? Unless I ask you to do that, I wouldn't, right? So that's why I remembered this one as a start, and then if I need the other one, I can find it by rearranging it. And you don't want to memorize more than one thing if you can just rearrange it to get the other one. Okay. So what do we use this for? We're going to do it for a 2 by 2, but the diagonalization, we're going to show what it's used for, a couple different things. Okay, so the first one is powers. So suppose I wanted to find A to the 10th power. And A is a 3 by 3. So that would involve taking A, you would do the first two, get the answer, do it by the third, get the answer, and your numbers are getting huge. Okay, so this is A, 10 times. You wouldn't want to do that. So the diagonalization helps you to do that. So how does that work? So we have A equals P, D, P inverse. Suppose we wanted A squared. Just A squared. So that would be P, D, P inverse times P, D, P inverse. Do you agree?
Yeah.
That's A twice. Simplify this. This is P, D, P inverse, P, D, P inverse. What happens here? These ones equal I. So then you have P, D, I, D, P inverse. Now I is like multiplying by 1. You don't need to show it when you multiply by 1. So this is the same as P, D, D, P inverse. What's D times D? D squared. So this is P, D squared, P inverse. Follow? Let's do cubed. So what if we wanted A cubed? P, D, P inverse. One more time. Do you see what happens? Do you see the P and the P inverse in between? So where are they? This one is an I, and this one is an I. So if we take those out, because they cancel, what do we have left? P, D, 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 and P inverse. Squash that together. Do you see it? Now, what if I wanted A to the 10 without writing that all out? Can you guess? Right? Okay. Now, why on earth is this easier? It's a multiplication, but there's only 3 instead of 10 matrices. And the middle one, D to the 10th power, is easy. Really easy, because it's a diagonal matrix. Powers of diagonal matrix let's put 2003. Okay, just a small one just to demonstrate. I'm not writing the one we actually have because it has a 0 in the top row. I want to show you what actually happens. The 0 makes things disappear. So say we wanted this to the power, well, squared first. So what happens? I think I showed you this before. You end up with 4009 when you multiply. So it is just the squares of those. If we wanted 2003 to the 10, it works out to be whatever those are. So for example, we're not going to do this all out, but if you wanted to do this, just cube, right? You would do the first two. And then you multiply it by this. You get 4 times 2 is 8. Here you get 0. Here you get 0. And here you get 9 times 3. 27, which is just 2 cubed and 3 cubed. Right. And if you kept going, you would multiply it one more time and one more time. So powers of a diagonal are just the diagonals, the main diagonal to the same power. All right. So we're going to do it for a 2 by 2 because I'm not going to find the inverse for that one that we just did, but so I'm going to write down A from our last question. So A was the matrix 4 minus 3, 3, 0, 0, 0, minus 6, 6, minus 5. And we found the diagonal Okay. Okay, so that's what we just found in the question. I'm not going to ask for the power here, but because to do the power, any power of A, we actually need to find P inverse, which would be legitimate on a final exam to find the inverse of a 3 by 3. So we've done that. It's actually on test 2 and test 3 to find the, so it would be legitimate to do that application. Okay, but we're going to do it in a minute for just a 2 by 2. The other application is this. Let's suppose I wanted to find so here's the question. This is all known. And I'm saying find this calculation here's Q, but don't find the inverse. Don't do a matrix multiplication, so do no calculations and find the answer to this. If they ask you to do that, that means that this is related to P somehow. So I want you to look at P and Q and tell me what I did. Okay, so column 1 and 2 are switched. Now in P, what was the eigenvector value for this first column? 0. And this one? 1. And this one? -2. Now what did I do? 1, 0, -2? Okay. So above Q inverse P inverse AP is equal to the diagonal. That's the same equation, just rearranged. Solve for D instead of solve for A. And I want Q instead of P. So I told you already you can put the eigenvalues in any order, but if you change the order, the D also changes. So here, Q inverse times AQ is the diagonal, but with the eigenvalues rearranged. So what would be the answer? We have to put the 1 first, then the 0, and then the -2. Okay? So I just called it Q because we already used the letter P. I could then do this. Find R inverse AR if R is So there's something else I told you, that when you put the eigenvectors in, they can be any multiple of that eigenvector. It doesn't have to be the exact one you found. It can be a multiple. So if they're asking this, then you already know the answer. You have to look at your P, your original P. So can we still see it? Let's move it down. Or we could look at Q, it doesn't matter. But here's P. This was 0, 1, and -2. What order did I put them in now? This is for -2. This one is for 0. And this one, although it looks different, is just a multiple of that. And so it's still okay. It doesn't have to be exact. It can be any multiple. This is still 1. You don't multiply it by 50. It's still 1. Yeah, because it can be any multiple. It doesn't matter. It'll still work the same. You can check it. You could multiply all of them by a different number, and it would still give AP would equal PD when you multiply. So here, R inverse AR will equal what? So the -2 has to go first, the 0, and then the 1. Nothing, no multiple of 50, nothing like that, because it can be any eigenvector in there, and it will still give the same answer. Okay, so that's another way we can use the diagonalization. Okay, so we're going to stop that.